Okay, fine. I think it's just a theoretical concept. So yeah, basically electrons moving equal to the atoms, and the atom will vibrate. Right. So yeah, if the current is more, then the energy dissipated is more, because power dissipated is given as I square into R.
Yes.
Okay. Okay. So this is a circuit diagram.
So this there's a source of potential difference over here, the battery.
Okay.
There are the wires which through which the current flows. There is a switch and the resistance.
This battery or cell.
This is a battery.
What is the difference between battery and cell?
So a battery is basically like a collection of cells, like many
Okay.
cells put together.
Okay. Why do you put many cells together?
Uh, Basically, increase the flow of current.
Increase the potential difference. When you add
Oh,
when you add two cells in series, okay, suppose the potential of this one is V1, potential of this two is V2. What is the potential difference between A and B? Suppose if we replace by a single cell across A, B, what should be the voltage of the cell to create the same effect?
no, there'll be a difference. This will have a high voltage, the previous one.
No, but I'm replacing by a bigger cell. So what should be the value of this voltage so that both the effects are same?
Oh, okay.
It should be V1 plus V2. Okay, because these two cells are connected in series. Okay, so
Right.
the rise from B to A is V1 plus V2. When I go from point B to point A, there is a potential rise, right? Here there is a potential rise of V2, and here there is a potential rise of V1. So the total potential rise is V1 plus V2. So the potential rise from B to A should be same in both the equivalent circuits. Okay, so similarly, if you have this cell as potential B, there are four cells, right? So the total potential difference will be 4 times V. So I'm getting larger potential difference.
Right.
And potential difference is the one which will drive the current. If you want more current, I have to connect more cells in series. Because the current here is total voltage divided by the resistance. Right? If you have to increase the voltage to 4V, then the current will increase 4 times. Right?
Okay.
So to drive more current, I need more voltage. To generate more voltage, I have to connect more cells in series. Right? That's why we use batteries. Okay. So there is a resistor here, and then there is this wire, metallic conductor. And what is this thing here in yellow?
So a compass needle?
Yeah, magnetic compass. So what does it do? Compass needle?
So it detects if there's a magnetic field. So if there is a magnetic field, then the needle will deflect.
Yeah, and what is a needle made of? Why does it deflect due to magnetic field?
It deflects the magnetic field. The needle will be made of some sort of material that is. It's made of some sort of metal, is it?
Just a bar magnet, small bar magnet. Okay. So if you put a bar magnet in magnetic field, it will respond.
Yes.
Okay. North pole will attract. Sorry, North pole will repel. Or North pole, South pole will attract.
Yes.
That force will create a deflection.
Okay. Okay.
Okay, so this is just an observation. There is a battery which is driving the current and resistance and a metallic conductor. And when the current is flowing, the needle is deflecting. Suppose you open this key. This key is called key.
Right.
Okay, if you close this key, current will flow. When the current flows, there is deflection. Okay, when you open this key, the circuit is broken, so the current is zero. So the compass is in a neutral position. So the needle is deflecting when there is current. Okay, so this is an observation which we have to understand soon. Okay, at the moment it's just an observation. When the current is flowing, the compass is deflecting.
Right.
Okay, okay. So this was discovered by this person who is dead. Okay, so he accidentally discovered. He didn't think this will happen. Accidentally, he took a compass needle near a current carrying wire and he found that it was deflecting. Okay, and he didn't expect that. He just found it by accident. Then you have to try to understand why it is happening so. Okay, but you know when you take a bar magnet close to another bar magnet, it will deflect, right?
Yes.
Suppose this is north and this is north. Okay, and suppose this is fixed and this is movable, so it will move this way.
Yes.
Okay, and if you bring another bar magnet which has got south pole like this and north pole like this, it will get attracted. Okay, so similarly, current, if there is a current carrying wire and I bring a bar magnet close to it, the same effect is seen. Suppose this is current carrying wire I, and I bring a bar magnet here. When the current is zero, say it is in this position. When the current flows, say it's getting attracted. Okay, and when I change the direction of current like this, then it is getting
Repelled.
Okay, so the same effect is seen in the case of bar magnet. Okay, I remove the bar magnet and replace by a current carrying wire. So we can see the effect of a current carrying wire is same as effect of magnet. Okay. Okay. So when the current is flowing in the wire, it is just a uh, electric phenomena, right? Current is flowing, it's a flow of charge. So it's basically electricity. When I have a bar magnet, it's magnetic field.
Okay.
So in some sense, electricity and magnetism are equivalent.
Okay.
Okay. All right. And now we need a concept of magnetic field. Okay. You know what is electric field?
Yes.
What is electric field?
So the field produced by the flow of the charges.
No, it is there in electrostatics also. No, even in electrostatics. Electrostatic means what? Charge is stationary, right?
Okay.
Statics means stationary.
Yes.
So even if a stationary charge, say plus Q, at rest, okay, it's not moving. There will be an electric field here. What is the symbol of electric field? What is symbol for magnetic field?
Magnetic field is B.
Okay, electric field.
Field. If I'm not mistaken, is it E itself?
Yeah. What is symbol for potential?
So potential difference would be V, voltage.
Okay, potential.
Potential.
Same B, okay. No problem. So potential difference is
V.
two points A and B. Okay. Potential is you can say
Right.
potential at point A.
A. Oh, okay, okay.
Okay.
Mm-hmm.
Right. So electric field. What is electric field? How is it defined?
Electric field. Just a minute.
Okay. Before electric field, if you have two charges, say Q1 and Q2, what is the force between them?
So F is equal to Q1 Q2 by R square. K into Q1 Q2 by R square. K is a constant over here.
Okay. R is the distance, right?
Yes, the distance between the two charges.
Okay. So this is the force. Fine. So from this, what is electric field? You can relate the definition of electric field to the force due to a charge.
Okay. So like a region around it?
If fine, but if it's due to no, if it's if we go to force on unit positive charge. So E due to say Q1 is equal to force on the unit positive charge. So suppose I want to find the electric field at this point, I bring up 1 coulomb say charge here, and whatever is the force, that force is equal to electric field.
Right.
Okay.
Okay. Okay.
So if you have to find a force on charge, say Q3 here. Okay. So force on Q3 is how much? In terms of E, E is known at this point. E is the force on unit positive charge. So what is the force on Q3?
So it'll be the one around E.
Okay, if force on 1 coulomb is E, what is force on 2 coulombs?
2E.
Yeah. So what is force on Q3 coulombs?
Would it be 3E?
No, Q3 into E. Charge is
Oh,
Q3.
right. 2E. Right.
Right. So if you know electric field at this point, if you have to find a force on a charge, any charge Q at that point, so it is Q into that electric field at that point. So that is the advantage of electric field. Once you know the electric field, I know what is the force on any charge.
Okay. Okay.
Okay. So what I can do is, suppose there is a charge here Q, and I want to find the force on Q2 here. Okay, let me call this Q1. Okay, I want to find force on Q2. So this I'll equivalently, I'll put a field here. Field due to say Q1. Q1 is the source of that electric field. Okay, and here the charge is there, Q2. So here I can get the force on 2 as by Coulomb's law. K into Q1, Q2 by R square. Okay, here I'll get the force on Q2 as Q2 into EQ1, because EQ1 is the, by definition, the electric field is the force on unit positive charge, right?
Right.
Then the force on 2 is Q2 times force on unit positive charge.
Okay. Okay.
Okay, now EQ1 is force between Q1 and 1 coulomb, right? That is the definition of electric field.
Yes.
So this is equal to how much then? K into,
So it's the same thing.
no, K, what is the second charge? Q1 is the first charge. Second charge is what?
It's 1 coulomb.
Yeah, divided by R square.
Uh,
So if I multiply this and Q2, I'll get the same thing, right?
yes.
Okay, so I am removing this charge in this second case. See, in the first thing, Q1 is there. Okay, the second thing,
Yeah.
I'm removing that Q1. Q1 is removed and it's replaced by its electric field.
Okay.
Okay, you cannot say force on Q2 is K Q1 Q2 by R square by Coulomb's law, and then Q2 into EQ1 by the definition of electric field. You cannot
Mm-hmm.
add both. Okay, the effect of
Okay.
presence of charge Q1 is captured in the electric field.
Mm-hmm.
Okay,
Okay.
once you do that, you remove that Q1.
Okay. Okay.
Okay, because the effect of Q1 is being included in the electric field. Or you don't
Okay.
consider electric field, just apply Coulomb's law between 2 point charges. Between 2 point charges. Okay.
Okay.
So this is the advantage of using fields. Okay,
Mm-hmm.
the effect of charge is being captured in the field. Similarly, in magnetic field, this okay here in the electrostatic, the source of electric field is a charge, right?
Yes.
So in magnetic field, what is source of magnetic field?
Magnet?
Yes. Uh, Magnet is basically in North Pole and South Pole, right?
Yes.
Okay, if we break this magnet into two pieces, so this will become North and this will become South Pole. And
They still have their individual north and south poles, will they?
but in electrostatics, we have two types of charges, right? Positive and negative.
Negative, yes.
Yeah, and they can exist separately. But in magnetic field, the source of magnet is a magnet. If you try to break the magnet, again you'll get a north and south pole. I cannot have individual north and south poles. Okay,
Right.
so that is one major difference between the electric field and the magnetic or electrical source and source of magnetic field.
Field. Right.
So this thing is called non-existent of magnetic monopoles.
Okay.
Non-existence of magnetic monopoles. Okay, uh, north-south is the combination is called dipole. Okay,
Mm-hmm.
monopole is either north or south separately. That's not possible. So this is called non-existence of magnetic monopoles. Right. So this is the source of magnetic field. Right. So the effect of this bar magnet should be captured by the B field.
Yes.
Okay. So suppose I bring another magnet here, there will be some force between them, right? So so the same second magnet I bring it here, but the effect of first magnet should be captured in the B field.
Me field, right.
So we call this 1, 2. This is the second magnet. And the first magnet I have replaced by the field produced by the first magnet. Okay. So this is the basic idea of using the concept of field. Okay. Right.
Okay.
So here there is a bar magnet, and what are these small circles? What do they look like?
Charges?
I also thought so. It is same as this one. Got it?
Uh, okay.
It's a compass to sense the magnetic field.
Okay.
Okay, it's a magnetic compass. These two are the vertical lines, and then there is a deflection, needle deflection. These two verticals
Oh,
are the reference lines.
okay, okay.
So that plus is the reference line of the compass. Okay, so
Okay.
so the magnetic field will deflect because of the magnet here. Okay, so and the direction of the reflection will be different.
Okay.
Uh, Suppose the magnetic needle is like this. This is North Pole. Okay. So when it is here, it will be like this. At this point, the North Pole will be here, right? This will be North Pole.
Yes.
Okay, here the North Pole will be like this.
Yes.
Okay. Suppose I assume take this as a direction of something. Okay, and I keep moving this needle. Okay, so it will show a direction. Okay, so here the direction will be like this. Here the direction will be like this. Here the direction will be like this.
Okay.
Okay, and now I draw a curve which is tangent to all these arrow marks. You know what is a tangent, right?
Yes.
What is a tangent?
So it's basically if we have a circle, we draw a line, so that thing will be a perpendicular. It basically is the point line through a point touching the circle.
Right. Tangent touches the curve at only one point.
Yes.
It need not be circle, any curve. At only one point. But but you just have to see this locally, because suppose the curve is like this, okay? At this point, the tangent will be like this. Okay, so locally it will touch at only one point. But if you extend it, it will go and cut somewhere.
Yes.
Okay, so you should not extend it. You just have to see the local behavior.
Right.
Okay, tangent means in that neighborhood, it touches only at one point.
Right.
Okay, but for circle, that's not a problem. Alright, so you have to draw this curve which is tangent to all these arrow marks. So this is that curve.
Okay.
Okay, so and you can put an arrow mark on that curve which gives the direction of the magnetic field. You can fix the direction of the magnetic field as the direction of the north pole of the magnet or the needle.
Okay.
Okay, like when you have x-axis, you take right hand side as positive axis, no? Positive direction, and left hand side as negative.
Yes.
That is just by convention. I can also take right hand side as negative and left hand side as positive.
Positive. Right.
That will be unnecessarily confusing because everyone takes the right hand side as positive. So, okay, it's just a convention. Similarly, you take the direction of the north pole as the direction of the arrow. Okay. It's a convention and you stick to it consistently. Okay, so if you place a bar magnet here, the north pole will be here.
Yes.
This will be south pole. So this is the arrow mark. Okay, and another thing is the strength of the magnetic force will keep on decreasing as you go far away, right? Because it's far away from the magnet, closer at nearby will be closer. Okay, so that information I can give with the length of the arrow. The magnetic field is strong. Here it will be small. If you get closer, the magnetic field is more, right? So I put a longer arrow to
Yes.
indicate the information that the B here is strong. Okay.
Okay. Yes.
Okay. Another way of conveying this information that magnetic field is strong is by the density of lines. If I draw a line perpendicular to these curves, field lines, the number of field lines cutting this line per unit area, per unit length, or you can see density of lines. Here the density of lines is more, right, compared to here.
Yes.
Okay, the density of lines is proportional to the strength of the magnetic field.
Okay.
Density of lines is proportional to magnetic field strength. Okay, so nearby the magnetic field strength is more, so the lines are closely packed, and outside it is far away. Okay, here it is closely packed, right? So here the strength is more. The value of B is more. But the direction is towards right. Here also the value of B is more, but the direction is, yeah, here also is right. Okay, so this is the idea of using field lines and how to draw the field lines. The same is true for electric field. Okay. See here, the electric field drops as r square, no? So here the electric field will be more, and here the value will go down, and far away it will be still less.
Yes.
Okay. So then the field lines will go like this, radially outwards. So nearby you can see the density is more. When you go out, the density is decreasing.
Yes.
Okay. So that conveys the information that electric field is dropping, and actually this is a three-dimensional thing. So it is a spherical shell.
Right.
Right? And surface area of a spherical shell is 4 pi r square. You remember, you know this formula? Surface area of a sphere.
Yes.
Okay. So density of line is number of lines divided by the surface area, that is 4 pi r square. Number of lines is fixed because that is same here. Here and also here, the number of lines is fixed. Suppose I'm in this particular case, the number of lines is 5 here, no? At a nearby sphere. At far away sphere also, if you take a full sphere, the number of lines is same.
Same, right.
But only the denominator is increasing as r square. Okay. So that's why the electric field goes as 1 by r square.
Okay.
Or the force, because force and both. Because force is nothing but just Q2 into E. There is no R dependence in Q2. So the R dependence of F will come from the R dependence of E. And the R dependence of E is 1 by r square. So the R dependence of F is also 1 by r square.
Okay.
Okay. Yeah. So the effect of magnet is represented by the magnetic field. So once you take the magnetic field, you have to forget the source of the magnetic field, which is the magnet.
Yes.
Which here I put for magnet one, I have put the field. So after that, I have to remove the magnet. The effect of the magnet is being captured by the field. Same thing we do for the charges. Once I put the charge, there is no. Once I put the field EQ1, there is no charge here. Q1 is charge here. Okay.
Okay.
Okay. And no two flow lines are found to cross each other. Okay. So when you are, suppose I want to draw the electric field line due to this charge Q1.
Okay.
I have to take a unit charge, 1 coulomb, and find the force on it. Okay. So the force direction will be like this. Okay. And the force direction here will be like this. Here it becomes smaller. And I draw a curve which is tangent to all these vectors. So that will be like this, right? And this is a field line, same as this one. Yeah. And another way of saying this is, if you take tangent to the field line, will give me direction of E, right?
Yes.
Okay. And suppose at this particular point, two field lines are crossing. Okay. Then there are two tangents, right?
Right.
That is not possible because for a given point, there is only one value of electric field.
Field, right.
So that's why the no two field lines will intersect. That is true for even magnetic field. Okay. Because if the magnetic field is intersecting, okay, then the compass needle will point in two directions, which is not possible.
Yes.
Because we get the direction of the magnetic field by taking this magnetic needle, and whatever direction it points, that is the direction we draw an arrow. Okay, and then we draw the curve which is tangent to all the arrows. So at a given point, there's only one curve crossing that point. If there are two curves, means there are two tangents. So there are two directions of the magnetic field, which is not possible. There is one direction. Okay, so this is a bar magnet, and iron filings. Iron filings means what?
So they're like crushed pieces of iron.
Yeah, small particles of iron. So when you surround this magnet by iron, and then you gently tap it, it will form like this. So this is matching with this field line picture.
Yes, matching.
This is theoretical. This is actually a theoretical understanding, and this is actually a photograph of what is actually happening. Okay, so you can see the iron filings aligning along the direction of the magnetic field lines.
Right.
Okay, right. So right now we have seen. Right now we've just taken the bar magnet and then see the magnetic effect of it. Right. Okay. Now
Right.
instead of that, we take a current carrying wire. Okay. So this will need to touched upon. So this is an electrical circuit similar to the one which is shown in the first one. A battery, key. Of course, the wire will have a resistance. Okay. They are not showing this. And the current is flowing. So what is the difference between the A figure and B figure?
The direction of the current different.
Yeah. Here the current is flowing clockwise or whatever, one direction. This is the direction of current. Here the current is this way. Okay.
Yes.
So in this wire is flowing like this. Here it is flowing like this. The direction of current is reversed. Okay. So when there is no current, the needle will flow needle in some position. When the current starts flowing, it is deflecting.
Yes.
Okay. Here, when the current is flowing, it's reflecting in this direction, in the opposite direction. Okay. So first conclusion is the effect of magnetic needle, which deflects in presence of another bar magnet, is observed even with the presence of current carrying wire. Okay. So in some sense, the current carrying wire acts as a magnet.
Right.
Okay. So that is an observation. And the direction of the current changes the, you can say, polarity of the magnet. Because the bar magnet, if we reverse it, the deflection of the compass will reverse, right?
Yes.
Okay. So similarly, when I reverse the direction of current, the deflection of the needle is changing. Direction is opposite.
Yes.
The direction of current is same as the changing the direction of the polarity of the magnet.
Okay.
So this is another thing. Same circuit. So this is a cardboard. The wire is passing through it. Some hole is made in the cardboard. Okay. So because of this current flowing, there will be magnetic field lines. Okay.
Yes.
When the current is flowing, it's acting as a bar magnet, right? Or some magnetic effect is there. So it's
Yes.
so the effect of a bar magnet is captured in the magnetic field. So similarly, the effect of a current carrying wire, I can capture it in the B field, magnetic field. So the magnetic field lines look like these dotted lines. Okay, so that we can, because when we try to do with the bar magnet, we figure out that the pattern of this ion filing is same as the pattern of the magnetic field. Right?
Yes.
So similarly, when you use the ion filing here, okay, the right picture, okay, the ion filings are getting in form of circles,
Yes.
concentric circles. Okay, so from there we can conclude that the magnetic field lines will look like this.
Okay.
These are B lines, magnetic field lines. Okay, concentric circles, and the density of the circles will be, as you go out, it will be less dense. Near this one, the B is more. Closer it's B is more. Here B is less. Okay, the figure is not drawn properly. So here the density of line should be more, and here the density should be less. Okay.
Okay. Yes.
Okay. Right. Okay. So there is one rule to get the direction of the magnetic field. This is a current carrying wire. This one, the straight wire. Current is flowing in this direction. Okay. So use your right hand so that the thumb will, you hold the wire in your hand. Okay. Inside your palm. So the direction of the thumb is should be along the direction of current. Okay. Then the direction of magnetic field is the direction in which the other four fingers curl.
Right.
Okay. So the other four fingers will form a give you a direction of a circle. Okay. And that is matching with this picture of iron filings. This wire, I have to hold it in my hand so that the thumb is in the direction of current and the direction of the magnetic field is along the, it will be in circles. It will form a circle.
Yeah.
Okay, so this is a rule for getting the direction of magnetic field. Here the current is downward, the thumb is downwards, and direction in which the fingers curl is this way.
Yes.
So it is relating these two directions, thumb and the fingers. So one is the current, other one is the magnetic field.
Yes.
Okay. Right. So in this case, the first one, the direction of magnetic field will be if I look from the front side, it will be this way. Is it correct? Thumb should be out of the plane of the paper and the fingers will curl in this direction. Got it?
Okay.
So thumb should point along this arrow. The fingers will curl in this direction. In this one, thumb is into the plane of the paper. Okay. And the fingers will curl in this direction. So this is the direction of magnetic field. So here it is anti-clockwise, and the second one is clockwise.
Okay.
Okay, because the direction of current is second, we should expect that the direction of magnetic field should be reverse.
Okay.
Okay, so if you apply that rule, you can see it's reversing because thumb is reversing. In the first case, the thumb is pointing out of the plane of the paper. You know what is plane of the paper, right?
Yes, yes.
Okay.
We can consider the paper.
Yeah, something is coming out from the screen and towards you, and into the paper means something is going into the screen from you.
Yes.
Okay, so in the first case, the thumb should point towards you. In the second case, the thumb should point into the screen or the paper, right? So from this, you get the direction of the magnetic field. Okay. Now, instead of a straight wire, you have a circular wire, circular loop, right? And there is a circular loop. Right? So I can use the same right hand rule. Okay, if you take a small portion of this wire, say from here to here, it's approximately straight, right? If you take a circle and if you take a very, very small part of it, okay, it will be approximately straight line. Okay, so in that I can point thumb in the direction of the current and the direction in which the fingers will curl will give me the direction of magnetic field. Okay.
Yes. Okay.
Here, in the top part, the current is coming out or going in. Suppose I assume this is the direction of current. We marked as positive. Let me see whether it's correct or not. So this is the direction of current. The current is flowing like this. Is that right? I'm assuming it's entering here.
Okay.
So it will go like this and go like this, right?
Yes.
Okay, so the direction of current is like that. So on the top, it is coming out of the plane of the paper. Here, the current is coming out in this topmost part. The current is coming out of the paper. So the thumb should be pointing towards me. It is not pointing correctly. Minus 3 lines of current. Okay, then you have to take the direction of current opposite. Okay, since he has put that on the top, he has put the circles in clockwise direction, right? So then the thumb should be
Right.
pointing inwards, right?
Yes.
The direction of current should be into the plane of paper. At this point, the current should be going in. Here, the current is coming out at the bottommost point. So the thumb is towards you. So in that case, this is the correct direction of B. Okay.
Yes.
So there's a minor mistake. It's not a problem. So here the current is coming out. Right. Another way to get the direction of magnetic field is, suppose I want to get the magnetic field at this point. Okay, I curl my fingers in the direction of current. Okay.
Okay.
And the thumb will give me the direction of the magnetic field. Now I'm getting the direction wrong.
Okay.
Now if you assume the current in the okay, the thumb should be towards the magnetic field. So this is the direction of thumb. Okay.
Okay.
This is thumb. So it is towards left. Okay. So that the current will go in the clockwise direction. So then the current will go this way. So in the top one, if the current is no. The current is clockwise, right? If it is clockwise, yeah. No, if it is clockwise, then the current is entering. Yeah, I think I made some mistake. See, the current is clockwise. Okay. Okay.
Yes.
If it is clockwise, means then it is entering the plane of paper. Everything is
Yes.
correct. Everything is correct. I made a mistake here. Okay. So it's entering here and then coming out here. Yeah. Yeah. Okay. Everything is correct. Think carefully. See, I have taken this direction as coming out, right? So according to the direction, the current here is entering. Forget the plus minus sign of the current in this figure. Whatever I drawn in the red one, this is the direction of current. Is that correct? The current is going this way. On top, it's entering into the paper. And the bottom is coming out of the paper. Okay, that gives me this direction of the B, which is correct. Given this direction.
Yes.
Okay, and according to
Yes.
this another way of applying thumb rule, the thumb is along the direction of magnetic field, and the fingers will curl in the direction of current. When you have a straight
Yes.
wire, when you have a straight wire, you put the thumb in the direction of the current. Okay.
Yes.
When you have a straight wire. When you have a circular wire, you put the fingers, the 4 fingers, along the direction of the current flow.
Yes.
And the thumb will give the direction of the magnetic field.
Okay.
There are two ways of applying the same thing. One is for the straight conductor, another for the circular loop. So here is the same picture. Here you can, on the top, you can see the current is. So here the current is going down, right? So if you consider this is a straight wire, the thumb is down, and the fingers will curl this way. So this direction is correct.
Okay.
Okay. So here, if you look, the current is upwards. So if you take the small portion of the straight wire, the thumb is around the current, and the fingers are curling this way. So this direction is also correct.
Okay.
Okay. So to get a magnetic due to a straight wire, the thumb should be in the direction of current. If you want to find the magnetic due to a circular loop, the four fingers should curl in the direction of the current. So, for example, the magnetic field lines here, it is in this direction, right? So that I can get by the all the four fingers curling in this direction. 1, 2, 3, 4. All these four fingers are curling in this direction, and the thumb will be in this direction. This is thumb. Maybe use the right hand.
Yes.
Right. So the key concept of this chapter is this due to this varistor. Okay.
Okay.
When I bring two bar magnets, the bar magnets are there is some force between the bar magnet and the second bar magnet. But if you remove the first bar magnet and replace by a current carrying wire, the effect is same. Okay, so in some sense, the current carrying wire acts as a magnet.
Okay.
Okay, and it's exactly so that you'll learn in higher classes. Okay, so in okay, one way of getting magnet is by these are naturally occurring magnets. On Earth itself, certain substances behave like magnets. They are permanent magnets. They are there everywhere, right? Fridge doors may be electromagnet, but some magnets which you use as a to stick something on the iron wall, right? For example, the flap of a mobile phone, they also have magnets. Okay.
Okay.
What about some cupboards? They have a magnetic, some magnet, right?
Yes.
They are permanent magnets.
Okay.
Okay. But instead of that, you can have a current carrying coil. Okay, and then pass it over some material, and because of the current flowing, it will act as a magnet. Those magnets are called electromagnets.
Okay. Yes.
Electromagnets, you producing the magnetic effect by a current.
Okay.
This is basically what the chapter is contained. Okay, some more things are there. We'll do it in next class. Right. So basically, there will be if you have two charges, two light charges, there will be repulsion, right?
Like charges, yes.
In electrostatics. So unlike charges, there will be attraction. Okay.
Yes.
So I can generate some force because of attraction there is some movement, right?
Yes.
So so basically some force is there. Similarly, magnet, if I try to bring it towards another bar magnet, it's repelling or attracting. So that's also can generate a force. Okay. So when I have a magnet and bring a current carrying coil near the magnet, there will be some force.
Okay. Okay.
Like this is a bar magnet, a permanent magnet, a horseshoe magnet. Okay. And this is a current carrying wire. When I bring it close to it, there will be some deflection. This red one is the magnet, permanent magnet, and this gray AB is a current conductor. Okay, the current is flowing through it because of the external circuit. Some battery is there and key is there. When you close the key, the current will flow, and when the current flows, it acts as a magnet, right?
Yes.
Okay, because current carrying conductor is like a magnet. So these two magnets there will be some interaction.
Yes.
There will be some repulsion or uh, attraction depending on the polarity. So there is some force generated because of this magnet and the current. So if I design it properly, I'll be able to generate. So here again there is a magnet and this is a current carrying loop. Okay. When I place this uh, these two things together, there will be some force between these two. Because of this force, it will move.
Yes.
Okay. What exactly happens with see in the next class.
Okay.
But this is the basic idea. There will be some force. We will bring two charges and also bring two magnets. Where one magnet I am producing by the current carrying wire, another magnet is this permanent magnet, or this magnet also can produce by passing a current. Okay. Doing Monday, Tuesday, Friday.
Yes.
Okay, fine. Then see you tomorrow.
Okay. Yes. Thank you.